This is the third and last example of Monte Carlo simulation. It's labeled here example 4 because this happens to be the fourth example in the textbook. There are a number of examples in the text, 6 or 7 or 8 of them, and they are worth looking at. I'm only going to do 3 of them here on the videos. Here is the example. What is the 90th percentile of the distance between 2 points chosen at random in the interior of a unit square? You can see off to the right here, I've drawn a unit square, and here are 2 points that are selected at random in that unit square. So obviously the x and y coordinates of this first point are uniform 0, 1s, and the x and y coordinates of this point are uniform 0, 1s, and here's the distance between the two of them. Now, if you think about what the possibilities are for that distance, the shortest possible distance would be 0 because those points could lie very, very close to one another. The largest distance you could be is if they're at opposite corners of the unit square, and that would be square root of 2. So we know that this 90th percentile is going to lie somewhere between 0 and the square root of 2. And since it's a 90th percentile, it's going to be closer to the square root of 2 than it is to 0. Before I started the video, I wrote a little program up here to help you visualize what's happening. And this one goes from 1 to 20, so I'm going to give you 20 line segments. And in each case, I'm going to generate 2 uniform 0, 1 x values, 2 uniform 0, 1 y values. PCH stands for plotting character. I'm going to use a solid dot as I plot the endpoints. And I'm going to keep my x limits between 0 and 1 and my y limits between 0 and 1. And what that will do is that way I will always have a unit square here. And type equals O is going to connect the two with a line. Then I'm going to call the sys.sleep function. And what that will do is that will have the system sleep for 1 second between each of the lines that are drawn. So let me go ahead and run this, and you'll see 20 segments appear, random segments that is, in the lower right-hand screen. You can see some of them are fairly short, like that one. That one's about a medium size, and occasionally you'll get longer ones as well. Some of them are horizontal, some vertical, etc. So that's just to give you an idea of what those random segments might look like. What we're trying to do is find the 90th percentile of the length of that random segment. So what we want to do is we want to generate a whole bunch of these segments, not just 20 of them, but say millions of them. Maybe we'll go with 4 million. We're going to really crank it up here. NREP is equal to 4 million. So we're going to generate a whole bunch of these segments. Here's the way I'm going to generate them. I'm going to set x1 to RUnif NREP. So that'll give me the first x values uniform 0, 1 value. Then the same thing is going to go for x2. And then we'll do the same for y1. This is a little bit different than the previous Monte Carlo simulations in that this particular Monte Carlo simulation is not going to need any loops. This one is going to be loopless. Now, we have 4 vectors, each of which have 4 million elements in them. And now I'm going to set the distance equal to, and this is just the distance formula, the square root of x1 minus x2 squared plus y1 minus y2 squared. And now what we have is we have 4 million distances, and there's only one statement left. This last statement here will be to first of all sort all those distances, And then what we want to do is we want to go 90% of the way out in that sorted array and grab that particular value of d, and that will be our estimate for the 90th percentile of the distance between the 2 points. Okay, so at this point we'll come back down here and set a seed. This time we'll use stream 5. And at this point we'll go ahead and execute those. You can see there's a little bit of a delay on each one of these, but that ran very, very quickly for having 4 million replications. So our first estimate is 0.859. Let's run it again. That one also rounds to 0.859. Let's do a third run. That one also rounds to 0.859. So at this point, with the 3 runs, I'm pretty comfortable putting out 3 digits as my estimate for that 90th percentile of the distance as 0.859. The interpretation of that number is, if I draw a number of these segments over here, about 90% of them will be shorter than 0.859, and 10% of them will be longer than 0.859. This is the 90th percentile of that length. This ends Monte Carlo simulation, and as I've said before in the book, there are a number of other examples which will help solidify your thinking on Monte Carlo simulation.